Hi everyone. In today's lesson, we're going to be looking at the last three types of chemical reactions. We already looked at a synthesis reaction, a decomposition reaction, and also a combustion reaction. We start today with a single replacement reaction. In a single replacement reaction, we always start off with a single element. And when I use the word single, I mean that it's an element that's not combined with anything else. In addition to having the single element in our reactants, we will always have a compound as well. And that's the pattern that we use to find a single replacement or to classify a single replacement reaction. And in this reaction, the single element will replace something in the compound, thus its name. Now, as a hint, you should know that if the single element is a metal, then it can only replace, oops, spelled it wrong, another metal. And same goes true for a nonmetal. If your single element is a nonmetal, then it can only replace a nonmetal. Right? So that's one of the big hints. And the single element has to pry apart the compound. Now, the thing with the single replacement reactions is that we need to rely on table J. So I need you to find your reference tables, pause the video if you need to, in order to determine if that single element is strong enough to break an octet. And table J is really the one table that will help us determine if a single replacement reaction will occur. All right, so let's take a look at examples. Now, table J, which is known as the activity series, is on page 5 of your chemistry reference table. And it works very simply. The more active or stronger elements are always at the top. And this goes for metals and nonmetals. And as we go down, 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 we see the least active metals and the least active nonmetals at the bottom. Now, here's the very important thing. The single element must be strong enough or more active to break up an octet. And if it's not strong enough to break that octet, then the reaction will not occur. So you need a very specific table to determine that. Now let's take a look at the first example. My single element happens to be Ag, which is a metal. Ag, if I look at table J, is at the bottom. Now, since Ag is a metal, I have to replace the metal in the compound. And the metal is considered the first position, because when we write formulas, the element that has the lower electronegativity value is in the front, and that's usually our metal. So I want to see where sodium is in compared to Ag. And sodium is way at the top. Since my single element is lower on table J, that means that single element is not strong enough to break up the octet that's already formed in the compound. And thus the reaction doesn't occur. So what we write here is no reaction. The only way the reaction can occur is if the single element is strong enough to break that octet. So let's look at it in the reverse. We know that sodium is higher on table J. And since it's higher on table J, that means it's stronger. It's specifically stronger than Ag, and a metal replaces a metal. So what sodium does is it takes the place of Ag. That octet is not strong enough to be held by Ag, so Na will take it. My products now become NaCl, and I'm just going to write the elements first and check it later, plus now Ag is by its lonesome. It now becomes the single element because it wasn't strong enough to keep its octet with chlorine. Now, as always, when we write formulas, we need to double check. Since this is ionic, I need to see its ionic charges. Na is +1, Cl is -1. I crisscross, and this is the right formula for NaCl, And now I need to remind myself Ag is monoatomic, so I don't need a 2 subscript for it. So this reaction occurs specifically because Na is stronger than Ag and can displace it or replace it in the compound. All right, now if there's a single replacement reaction, then there's going to be a double replacement reaction. In a double replacement reaction, what makes it different from the reaction we just saw before is we always start off with a compound and also another compound. And instead of replacing, this is more of a switching. We're going to switch partners. The same rules really apply. The metal will specifically switch with the metal, and the nonmetal will switch with the nonmetal as well. The other thing to know about double replacement reactions, and we're not going to learn this in this topic, the next topic, we also rely on a table, specifically table F, to determine if this actually works. For our purposes right now, we're going to assume that it always works. And we have to assume the same things. We have to believe or know that the metal portion is in the front. So what happens is A replaces C, and then they switch partners. So now A gets placed with D, and C is the metal, so it goes first, gets placed with B. So they switch their partners. Now let's take a look at a real example. AgNO3 plus NaCl. I know it's a double replacement reaction because I'm dealing with a compound and a compound. The first thing I'm going to do is I'm going to find my metal position, or my metal. In this case, it's Ag, and it's Na. And I want to switch positions or places. So Ag will now get placed where Na is. Na now goes where Ag is. So my products end up becoming Na, NO3, and the metal has to be written first, plus AgCl. Now, since they're both ionic, I have to double check to see if the formulas are written correctly. Na is +1, NO3, if you look at table E, table E, it's -1. I crisscross, formulas are okay. Now Ag is +1, Cl is -1, okay, that formula is okay. You always have to check the formulas after you determine the products. All right. The final type of reaction that you might encounter when looking at chemical reactions is now known as an acid-base reaction. An acid-base reaction is a special type of double replacement reaction. But it has something specific that denotes that it's an acid-base reaction. Now, since it's a special type of double replacement reaction, we are dealing with a compound and also another compound. So that's the first thing we can recognize. But these compounds are specific. We're always dealing with an acid, and we're combining it with a base. I know it's an acid specifically because the H is in the metal position. I know it's a base because there's an OH in the non-metal position. Those are the two indicators that tell me that it's an acid and a base. But there's even something more telling. In an acid-base reaction, you always end up with water and also an ionic salt. Those are your constant products in an acid-base reaction. So even if you don't recognize that it's going to be an acid and base, you should recognize water. Now, water is written in this way because when we switch partners, I'm going to show you what it looks like. But you could easily write the products as H2O plus the ionic salt afterward. That's still acceptable. I just want to show you why it's HOH in the beginning. So let's take a look at an example. I have HCl and I have NaOH. So if I didn't know, I can tell you right now, this is an acid. It's got the H in the front. And NaOH, that's my base. Now, since it's a special double replacement reaction, or a special type of double replacement reaction, all I'm doing is I'm trying to replace the metal with the metal. So my H takes Na's place, and my Na takes the H's place. So I end up coming up with a product that looks like this. I have NaCl, metal always goes first, plus when I switch the other partner, I have HOH, which is really just water. Now, since I have ionic substances, I need to double check the formulas. Na is +1, Cl is -1, this formula is fine. And now even HOH, I need to double check. H is +1, OH is really -1. If you remember from table E, I crisscross the formula is correct. So this becomes an acid-base reaction specifically because here's my water, and you can write it as H2O if you want to, and here's my ionic salt. Okay, that's it for now. I'll see you in the next lesson.